In this course, we'll be talking about graphics and rendering considerations for VR. Before we get started, make sure you have downloaded our project file, which can be found in the link below this video, as we have prepared some examples of the topics we will be discussing in this course. Modern graphics cards can render complex 3D scenes with several different methods. Each has different strengths, so there's no right answer for which method you should choose. It will ultimately depend on the particular constraints of your project. Considerations we'll need to make include how many milliseconds we are willing to spend on each frame and at what resolution, how many lights per pixel we need and our preferred shadow method, how complex the materials are and which anti-aliasing method we should use. Unreal Engine offers multiple choices on how to solve the problem of jagged edges, but it is a project setting that affects your content and performance. We will discuss a few of these properties and suggest a good choice when it comes to VR. The recurring pattern here is to favor performance over flexibility. This is important because the best quality VR experiences typically have a high resolution and a high and stable frame rate. Classic forward rendering is how the early 3D graphics cards were meant to be used. Geometry is rendered with triangles. For each covered pixel, the GPU has to compute the final RGB color based on textures, material attributes, and lighting data. The performance per object was dominated by how many lights touched it. So for an outdoor scene, sunlight would be a cost incurred on all objects, but other lights are trickier. For control and performance, it is common practice to limit local lights to the attenuation radius. This allows developers to limit the number of lights an object is affected by. The lighting solution has to be more conservative. Even if the object is only barely touching it, the whole object needs to be rendered with one more light. This situation got much better with defer shading, where lights are called at the pixel level. We'll discuss this at greater lengths later in this course. There are many different defer rendering techniques. They all rely on storing data in a screen space aligned texture or render target. That means for each pixel on the screen, there is a texture that stores material attributes like material color, roughness, and surface normal. Some defer techniques only require a few channels. For example, defer shadows and fog simply need access to the Z buffer. Something all deferred techniques have in common is that they read from those attributes in the following pass, effectively decoupling itself from the material shaders. This allows for simpler and more elegant code which can result in better performance with scenes of high complexity. The downside comes with the need to read and write more memory. This has more of an impact at higher resolution and an even larger impact on low bandwidth hardware like mobile VR. Classic defer shading renders in two passes. First, all objects get rendered with a pixel shader outputting material attributes and geometry attributes into the G buffer. In the following defer passes, the shading is computed using the G buffer and lighting information. Because it decouples material complexity from lighting complexity, defer shading offers simplicity and elegance, as well as performance when using complex materials with many lights. One problem to note with defer shading is anti-aliasing. It is possible to render the G buffer using MSAA, but it adds complexity and adds even more to how much memory we will need, which reduces performance. And it is not currently supported by the Unreal Engine. Temporal anti-aliasing, or temporal AA, is a modern solution to this problem, but it requires a few frames to converge to a good result. That means content that wasn't on the screen before will appear blurrier for a few frames until it becomes sharp. Furthermore, fast movements or motion over noisy content can result in smearing. Temporal AA is very attractive as it works with defer shading and it fixes more aliasing issues than MSAA, such as specular aliasing. The method relies on feedback with full screen buffers, giving it a higher performance impact for VR. FXAA, or Fast Approximate Anti-Aliasing, is another modern solution to the same problem without the restriction of delayed convergence. These two anti-aliasing techniques rely on reading back render target contents and therefore suffer on mobile because of its limited memory bandwidth. So defer shading offers great benefits when using many features, but for VR, we have to target high resolution and high frame rate, so we have to be very selective on the needed features. As it turns out, forward rendering can be modified to provide a good feature with less of a performance impact. Cluster forward rendering is a modern twist on the classic method that is used in UE4 when choosing forward. By using dynamic branching and a per-frame light hierarchy, it allows for efficient light culling without a large performance impact from the intermediate buffer, such as the G buffer, directly outputting an RGB color. This avoids wasting memory bandwidth, and as an added benefit, it allows the use of the GPU built-in hardware anti-aliasing, which is MSAA. Anti-aliasing can be achieved by rendering an image in higher resolution. Imagine doubling the image size on the X and Y axis and downsampling. Doing this would be much slower as we need to compute and store 4 times as many pixels. MSAA is more efficient as it avoids the 4x fragment shader cost and duplicates the color values into 4 subpixel regions, depending on whether a primitive covers the subpixel. The additional subpixel saves the fragment shader execution, but it still uses 3 times more memory. This means MSAA only solves primitive aliasing, but has no effect on aliasing from textures or shading. Texture aliasing can be solved by using texture bitmaps and high-quality filtering. Note, UE4 disables bitmap generation for non-powers of 2 textures. This not only causes aliasing, but also can render slower. So make sure your textures are to the power of 2 in size on the X and Y axis. Example sizes would be 256, 512, and 1024. Keep in mind that they don't have to be square either. An example of this would be 256 by 512. Specular shimmering is a form of shading aliasing that MSAA won't solve, but UE4 implements technique that fixes specular shimmers with the composite textures features. You can find more information on composite textures in the link below this video. When switching an application from deferred to forward rendering, you might not see as much of a performance benefit with complex scenes. When reducing features, the benefit becomes clearer as you analyze the scene. For example, using reflections only on some objects like a mirror, but not on a doorknob, or making sure your skybox doesn't receive shadows since there will never be any there. If you target very high-end PCs and complex visuals, you might want to consider deferred with FXAA. Keep in mind that Unreal Engine 4's forward renderer has a limited feature set. Some of those features would have a high performance impact in a forward renderer and should not be used anyway. Others just might not be implemented yet. A long time ago, it was possible to render scenes with only a few handwritten shaders, but this became inefficient and tedious when it required more and more features. Unreal's method of choice is to essentially write an Uber shader implementing the general case and having shader variants, known as shader permutations. This is generated automatically. This can save programmers time and provide efficient shaders, but note that it results in long compile times and more memory required for the shader variants. If you're programming a new application for a mobile platform like Quest, you may be using a lighting model that is much simpler than the standard model. In this case, it is important at the start of your project to go into the project settings, rendering category, and uncheck most of the sophisticated shader permutations. Some of these features are possible if used with care, but it is better to start with them off by default for mobile since they may cause long compile times and a large project package size. Forward shading suffers from this problem more as it packs more functionality such as shading, shadow, light types, material types, and tone mapping into a single shader pass. The first shading splits material attributes, lighting, and tone mapping into different passes, making this much less of a problem. To toggle features, you can either use dynamic branching in the shader or compile specialized shaders. In many cases, this is handled by the Unreal Engine, but when you use materials with static switches, you add another multiplier to the problem and you might have to deal with it. Generally, it's good practice to use a few materials and reuse them often. It makes optimization much more effective and also will allow the GPU to render more efficiently because it doesn't have to switch shaders as often as when we use many different materials. These mostly impact CPU performance and are much more apparent on mobile hardware like the Quest or low-end PC virtual reality applications. This graph shows how the CPU render performance impact on the y-axis increases linearly with number of objects on the x-axis. The steepness of the graph depends on the type of draw calls. If they share the same shaders and material attributes, you get a flatter curve, and that allows for more draw calls and objects at a fixed computational budget. Something to keep note of is at 90 FPS, you only have 11 milliseconds CPU time before you miss a frame. Now let's talk about lighting. Lighting is one of the highest impacts to performance for rendering in VR. This is especially true for mobile rendering, as lighting not only comes with a massive performance impact, but you are unable to adjust any of the properties at runtime. Even for VR running on a PC, it's best to optimize your scene by reducing the number of dynamic lights. Lights are categorized into 3 types: static, stationary, and dynamic. Static is the least computationally expensive method for lighting a scene, and for that reason, most of our lights will be using this method. The static light contribution is simply added while light mask computes the indirect lighting and baked into textures, meaning at runtime there is a fixed performance value to render any number of those lights. This baking process happens during development, and therefore only affects your iteration time and how much space the project uses. Static lights can have any color, brightness, or be any of the 4 predefined light shapes: point, directional, spot, and rectangle. They can also calculate shadows and indirect lighting. A good lighting artist can make a very convincing scene with only static lights. Static lights are the high performance but low quality choice. They don't affect dynamic objects. For dynamic objects, Unreal approximates them and then stores the ambient lighting. This best guess lighting is applied to movable objects. Dynamic lights do all their calculations at runtime. Because of this, it's best to minimize dynamic lights as often as possible. Good use cases are objects or characters that move, like a flashlight or torch. Dynamic lights cast dynamic shadows that are very computationally expensive. When using dynamic lights, avoid dynamic shadows whenever possible. Dynamic shadows are implemented with the shadow map rendering technique. This method requires an extra rendering pass with all shadow casters that are in the shadow influence area. The performance impact per frame for this can be significant, so only use this option if urgently needed. Stationary lights have behaviors of both dynamic and static lights. They cast light on all objects, which show up in the surface details of the objects. They can also create pre-computed bounce lighting. It's important to note that whenever stationary lights or dynamic lights overlap, the renderer needs to do a lot of extra work, and you can only have 4 overlapping stationary lights before they are automatically converted to dynamic lights. You will see a visual warning in the editor when this happens. On PC, make sure to define a max render distance for dynamic lights, and try to reduce the influence radius as much as possible. What this is referring to is, here's the max draw distance. It's a pretty big unit. I think 500 would be that the light disappeared, and then if I move closer, it shows up. So there is a distance at which it will just turn off. And then when you put it back to 0, then that basically disables this max draw distance. This feature does not work on Quest. When baking lights, it's also important to place reflection captures in the world. Reflection captures take a 360 snapshot of your scene and apply the lighting details of that snapshot to dynamic and static objects. Note that when doing this, you want to make sure the reflection captures are not set to capture every frame. In our Course 2 map, we have the center area describing the different lighting sections. We'll also see we're getting warnings of too many movable lights with shadow casting disabled, specifically for the stationary and dynamic areas. For static lighting, the difference between it and other lighting is how shadows get baked into surfaces and what it looks like when you move those surfaces. Here's a static light. That means this is baked, and then I'll just move it. The moment they're moved, basically their light maps gets invalidated. Unreal would keep track of whether or not its light map, which is the static lighting information it has, is valid or not. The moment you move something that's static, it's not valid, and you will have to rebake the lighting. Once you rebake it, then it's gonna look correct. Before anything can be drawn to the screen of an HMD, Unreal needs to determine what is going to be rendered in the first place. The idea is, if an object in the scene isn't going to be seen by the player, then it can be removed from the render. This can save both CPU and GPU time. The GPU time is reduced as less triangle need to be rendered, resulting in less computations and memory access time. On mobile GPUs like the Quest, this can even manifest in battery savings. CPU time is reduced because less data needs to be set up by Unreal Engine and sent to the graphics API. With older graphics API like DirectX versions before 12 and OpenGL, there is another performance impact for the CPU on the graphics API and driver side, over which the engine has little control. This is where DirectX 12 and Vulkan can provide good savings, as these give us a little more control on how the rendering is being handled. View frustum calling tests a tight pre-computed bounding box around each object against the view frustum. The view frustum is defined by the screen edges and the camera location. For VR, the engine can compute a single frustum for both eyes. You can ensure efficient view frustum calling by creating large level structures out of many objects with tight bounding boxes. But keep in mind that splitting up the geometry into too many meshes can backfire and increase the draw call count and CPU time, which reduces performance. A general guideline is to have more than 300 triangles for most meshes. Another note is that if your scene is composed of smaller objects that are used multiple times, you can batch them together in order to render them in a single draw call. This can increase savings, but note that they are all drawn together even if some of these objects are outside the viewing frustum, which could ultimately impact performance as well. Occlusion culling can provide further resource savings, but this comes at a higher performance impact. Occlusion culling is essentially a real-time check of whether an object is potentially occluded by other objects, so our apps knows not to render those objects because we can't see them, and thus increasing performance. For scenes with little occlusion, like a detailed room, you won't be able to gain much performance with occlusion culling. The default Unreal Engine configuration works well for complex scenes, but our content might benefit from adjusting or even disabling it. Ideally, you should profile your content and pay attention to the performance impact over multiple frames. Unreal Engine's occlusion culling might distribute its work over multiple frames to avoid spikes in your CPU timings. And then it's under rendering culling and then occlusion culling, disable as an implicit recommendation to disable it. We'll have to optimize our content more to allow for some buffer to not have those spikes causing hitches, which we go into more detail in course 10 and 11 of this learning path. In those courses, we will also identify profiling tools and how to apply optimizations. For the sake of this tutorial, we will leave this enabled. Though when you get to optimizing your app, try experimenting with these settings, as in some cases having it disabled can benefit your app. In the event that we wanted to disable occlusion culling, whether for performance or other reason, a substitute for occlusion culling is called precomputed visibility volumes. These are actors that we need to place in the scene. They can be found in Place Actors. Search for precomputed visibility volume and drag it into the scene. You see a green cube in the scene which needs to envelop the play area of the level. We can place as many volumes as we need to cover the space. Once they have been placed in the scene, we need to build the map, which will calculate the lighting and pre-compute the visibility data. But before we do, we need to enable pre-computed visibility in the world settings. In the pre-computed visibility section in World Settings, you can adjust the visibility cell size, which is the size of the individual cells used in visibility calculation. A smaller visibility cell size corresponds with better coding efficiency, but generates large amounts of data which results in large memory consumption and build time. Once it's finished building, the level will contain a number of smaller volumes that have been traced for visibility of objects. This process is predetermining if an object is in view or not. Pre-computed visibility volume is essential for classic mobile games and extremely useful for reducing draw counts in VR titles. In the next module, we will be discussing material considerations for VR.